really drink from that. Every so often in the news, we hear about a city whose water supply has become contaminated and the residents are taken ill. Take Walkerton, Ontario, for example. In May of 2000, 7 people were killed and approximately 2,300 people were taken seriously ill when the city's water supply became contaminated with E. coli. One of the main causes of this tragedy was inadequate quality control of the city's water system. The quality control in Walkerton consisted of 2 tests. The first test was carried out on a daily basis and measured the levels of chlorine present in the water. The second test was carried out on a monthly basis, where samples were taken and sent to a laboratory for further testing. The evidence collected after the tragedy suggests that neither of these tests were carried out to the specifications outlined by the Government of Ontario. These are some of the issues we seek to remedy with this project. My name is Tyler Hewitson, and with me today is Matthew Runyon, Brandon Buckrott, and Evan D'Souza, and we proudly introduce to you Trusted Waters. Trusted Waters is a photonics project that uses fiber optics in a new and innovative way. Trusted Waters is far-reaching. We envision an implementation that monitors the water supply of an entire city. Nowadays, fiber optic cables are starting to be used in a variety of sensing applications.
But how is this sensing achieved? How does one turn a traditional optical fiber for communications into an optical fiber for sensing? Well, there are 2 main modifications that need to be made. In the most basic sense, an optical fiber consists of 3 components, or 3 layers: core, cladding, and a protective sheath known as the jacket. In order for one to realize an optical fiber sensor, one must remove a portion of the jacket, such that the 3rd layer becomes the surrounding medium. In this way, any light that is in the cladding can then probe its environment and, more importantly, be affected by it. But how do we get light into the cladding? This gives rise to the second modification necessary, which is the addition of something called a fiber Bragg grating, or FBG. This component is a small piece of glass or plastic, which has had its index of refraction periodically perturbed by a pulsed laser. It is placed within inside an optical fiber core at an angle or tilt with respect to the optical axis, hence tilted fiber Bragg grating, such that diffraction can occur. This diffraction enables any light guided in the core to be efficiently coupled into the cladding. You can see a picture of these cladding modes, or the optical response of our optical fiber, in the figure behind me. These are actually 2 optical responses superimposed on one another. The blue trace corresponds to the optical response when the fiber is submerged in pure water, which has an index of refraction of 1.315 at 1550 nanometers. And the red trace corresponds to the same pure water sample, only with a 50 ppm concentration of chlorine introduced to the system. Upon a closer look, one can see that these optical responses are not the same. The cladding modes that are sustained, they're sustained at different wavelengths. You can say that the wavelengths have been shifted, and we refer to this as a spectral shift. This spectral shift can be quantified for a series of sample concentrations in a given calibration. Then subsequent measurements can be then correlated to these sample concentrations, and this forms the idea or the basis of our sensing.
With the current system configuration, the system must know the contaminants ahead of time, so the optical response can be compared to predetermined optical responses. In this project, a focus was placed on common household products, as these products are most common in municipal water systems. Some of the contaminants targeted for study were chlorine-based bleaches, dish soap, table salt, and pure sodium chloride. Various concentrations of these contaminants had to be carefully measured and monitored in order to provide a good calibration in terms of spectral shifts for the system. These spectral shifts must be taken with respect to some optical baseline. This optical baseline is established by measuring the response of distilled water. Once this baseline was established, careful measurements were taken to determine known masses and volumes for each contaminant. These masses and volumes were then added into a known volume of distilled water to give the desired concentration for testing. The optical response of the contaminants at the desired concentration was then captured from the OSA and stored in the program for later comparison. This process was then repeated while changing the concentrations of the contaminants in the solution by adding additional volumes of distilled water. This method associates concentrations to spectral shifts, thus providing calibration needed for the system.
How is this system implemented? Well, we require 5 materials: a broadband source to input light into the optical fiber, an optical spectrum analyzer in order to display the optical response, an optical connector to connect these 3 devices, and a laptop to run the detection software. The advantage here is the portable nature of these devices. We can reach rural communities for on-site testing. Of course, there's the stationary nature of these devices, which allows us to implement sensors into irrigation systems, such as wells or inner-city plumbing, to have automatic detection of contaminants and raise an alarm. Who is our competition? Well, in North America, the oxidation reduction potential meters, or ORT meters, are what's popular. The TFPG system has 3 distinct advantages. The first, the response is almost immediate. The limiting factor is the communication between the OSA and the laptop, or the frequency at which the software pulls the OSA. An important advantage to note is that the TFPG has unbiased detection. The only condition is that the contaminant changes the index of refraction of the surrounding medium. The final advantage is that the TFPG requires limited maintenance, and if damaged, the damaged portion can be removed and a new section of fiber can be implemented with minimal impact. But when discussing reliability, accuracy is an important point. Here on the slide, we can see 3 water samples taken from here on campus compared to a pure water baseline. The shift means that the water samples taken from the taps have a higher index of refraction. This is due to fluoride, calcium, and other minerals in tap water. Under the same test, the ORT meter cannot perform as well. This is due to low strength in the ionic bonds. This causes long stabilization times and incorrect results. This accuracy seems unacceptable. Some would argue cost, but what is the cost of the system compared to human life?
As you can see here on the slide, the most expensive costs are the one-time purchases of the broadband light source, the optical spectrum analyzer, and the computer and software to process the data and display results. This one-time instrumentation cost is enough to monitor an entire city, making the cost compared to the scope of coverage inconsequential. The other costs, like the fiber, the couplers, and the gratings, are even smaller. These would be the only possible recurring costs due to maintenance of the lines and replacement of possible damaged broken gratings. These smaller costs also make it cheap to expand the system to cover a greater area, especially considering that the cost of the fiber is the cheapest cost at about a penny a meter, making long runs of fiber very economical to install in the desired water system. This makes sense since glass fibers are just silica, sand, one of the most abundant materials in the Earth's crust. It's literally dirt cheap. Another area where cost can be minimized will be on the labor used to monitor the system. We've developed a simple interface that makes it possible for someone with knowledge of fiber or without knowledge of fiber optics or the underlying operation of the system to keep an eye on the quality of the water being monitored. This interface will alert the operator when a tunable detection threshold is crossed as a result of the spectrum of the water being monitored shifting away from the pure water reference. So the spectrum on the screen here shows the difference between the pure water spectrum and the water sample spectrum under test. As the sample spectrum shifts away from pure water, the difference will increase, eventually crossing the threshold of detection and alerting the operator to potential contamination. The type of training that this operator would need would be maybe an introduction to the operation of the actual system and safety training due to the use of the Class 3B laser light source in the system. This saves costs because the operator doesn't have to be a highly trained individual and doesn't require a high salary. We've also developed a more complex interface to show more detail about the interaction between the pure water reference and the spectrum of water being monitored. The main window here shows the full pure water spectrum in blue and the water being monitored in white. The 2 windows on the left show close-ups of the peaks around 1530 nanometers and 1540 nanometers. And the window on the right shows the wavelength shift and index of refraction for those same peaks. This interface was developed for someone who has more knowledge of the inner workings of the actual system and wants to check the actual wavelength shift and its corresponding index of refraction in order to do more in-depth analysis or to troubleshoot the system.
Trusted Waters is in its infancy. Given more time for development, 2 obvious extensions come to mind. First, instead of using a single fiber for sensing, which we have a working prototype for, one could use multiple fibers to give rise to an optical fiber sensing array. This has the distinct advantage of covering a larger area for detection. It can also provide topographical information as to the source of any impurities in the system and how it's diffusing throughout it. Another extension would be enhanced automation. In the event that a threshold violation occurred due to a large impurity, an automatic notification can be sent to the appropriate authorities, such as the Spill Action Center, such that the issue can be dealt with immediately. In addition to what was discussed today with respect to water quality, there's also been an analytics software model developed in MATLAB. This software model is able to simulate the optical response of any three-layer fiber system. It needs to be specified by layer thicknesses, indices of refraction, grading properties, and the spectral range of interest. This software model has many applications, not just here, such as biomedical engineering, civil engineering, and pharmacology. And with that, my colleagues and I will conclude our presentation. Thank you for your time.